Thank you, Sandrine, for the introduction. I'm MORITZ ESR3 of the FLOAWER project. Now we have a fairly big jump from hydrodynamics going to lidar measurements. And my work in general is on using nacelle-based lidar measurements on floating wind turbines for different applications. Mainly, I am working now on using this lidar inflow information for monitoring applications, so load monitoring. Today, I will talk about a specific study we have recently published, which is more about understanding the measurement itself and understanding the motion influence in the lidar measurements. So quantification and correction of motion influence in nacelle-based lidar measurements. I will go through that in the next minutes. A little bit of motivation, why this is interesting or why we looked into that. Inflow conditions, as you can imagine, differ for floating wind turbines from those with fixed substructures due to the dynamics of the floating platforms. And if we want to measure the inflow of floating wind turbines, we need to be aware of that and see what kind of influence there is from these motions on our lidar measurements. So I'm talking about this setup, which you can see in the nice picture. This is the Ideol FlowGen demonstrator wind turbine in Brittany, and we have installed from University of Stuttgart, we have installed our nacelle lidar on this turbine. In this setup, I'm talking about inflow measurements, so the lidar is looking forward into the wind field. Just as a side note, no, this lidar is turned around, and we are doing a wake measurement campaign also on this turbine. So if we are able to understand the inflow measurements, as I said, there are several use cases which are interesting. Is first of all, obviously, turbine control, which uses this information. But as I said, there are also other possible applications, performance monitoring, power curve assessment, of course, and what I'm also working on is load monitoring. So just as an introduction, what kind of influence is there from floater dynamics? So first of all, if you think of the lidar pointing into the wind field, there are changing beam directions. And this means there's different projection angles between the lidar beams and the vector of the wind velocity, and this changes our measurements. Then second is, if the turbine is tilted backwards or forwards, we measure simply at a different position in space, and this can make a difference, especially if you think of sheared wind profile, for example. And then there is translational velocities of the nacelle, which is coming mostly from the rotational degree of freedom of the floater. So the nacelle is moving back and forth and also side to side. These are the main effects. And how does this look like? This is a data example from FlowGen, so real data. You can see on the time series plot, the red-orange line is the floater pitch signal measured, and the blue line is the reconstructed horizontal wind speed from the lidar. So you can see obviously there's something going on, and there's a strong correlation between those signals, and that's also obvious from the frequency analysis. So we need to look into that. How did we do that? We have some measurement data from the lidar, but we are lacking a reference measurement in this setup, so there's no mate mast or comparison measurement. So we first I did an approach which is based on modeling the measurement, and I did two different ways. One is using a numerical model simulating the measurement. Basically, we are creating synthetic turbulent wind fields. We simulate floater dynamics with OpenFast. So we get the 6 degrees of freedom of the turbine. And then we couple this to our in-house lidar simulator, which we have developed in Stuttgart, and simulate the lidar measurements under the 6 degrees of freedom. And if we do that, we can do a statistical evaluation of the simulated measurements, so calculate errors and so on. And the second thing I did is developing a simple analytical model where we have very simplifying assumptions. We are just modeling the wind field by a power law profile, and the floater dynamics are just represented by harmonic oscillations. And why we do that, we end up with a fairly simple set of equations describing the measurement in the end. And by having this analytical representation, we can apply GUM methodology. It's a guide for the expression of uncertainty in measurements, and directly get an analytical estimate of uncertainty in measurements. So looking at some results of this, first of all, mean error or bias in the measurement. So time, when we look at time averaged values and ask ourselves, is there a bias in this time averaged wind speed measurements? Using our models, we can do this kind of plot these color maps, and this is kind of a parameter study. So we can basically evaluate bias in the wind speed measurement as function of different dynamic parameters of the turbine and environmental parameters like the shear exponent of the wind field. We don't have to go through the color maps in detail. So the takeaway from this parameter study is for the mean error, we have underestimation of wind speed due to the rotational pitch displacement. So turbine moving back and forth, looking up and down, and there is basically a coupling coming from the nonlinear shear profile, which ends up in underestimating the wind speed. And we have, or might have, an overestimation of wind speed due to the mean pitch angle of the turbine. So floating turbines, especially the SPA-type floaters, they operate in a condition where the turbine is tilted back a little bit. So the lidar is looking more upwards than you think from the upright position, and you end up at a higher height basically. And again, if we have a shear profile, this makes a difference. So we overestimate the wind speed in this case. So why is this important? As you know, time averaged wind speed estimates, like 10-minute averaged, it's mostly relevant for applications like power curve assessments or power performance monitoring. And there, bias in the range of 0.1 meters per second can already make a difference. So we thought of how we could correct for this bias. And the simple idea is we are using this analytical model to calculate a correction value based on the dynamics parameter for each condition. So we can calculate, using the analytical model, we can calculate a correction value, which is a function then basically of the wind speed, shear exponent, mean pitch angle, and pitch amplitude. And we can basically subtract this value from our lidar measurements. And this is the result of this study for two different floater types. So the first line here is FLOAGENT, and the second one is Windcrete floater concept, which is a SPA-type floater. And the rows here are different shear exponent values in the wind field. And if you look first at the solid green line here in the first line for FLOAGEN, the solid green line represents pitch amplitude over different wind speeds here. And you see that the FLOAGEN floater has relatively high pitch amplitudes, around 5 degrees, but low mean pitch angle. So the dashed line is the mean pitch angle. And what, as we expect also from the parameter study, we see that the blue line, which is the uncorrected values, shows negative bias, especially for the higher wind speeds. And finally, the red line is the corrected values, so applying our correction values, and we see that we are quite good with compensating for this bias. A bit the other way around is for Windcrete floater. The mean pitch angle of the Windcrete is quite high, especially around the rated wind speed, where the thrust force is the biggest, but it has low pitch amplitude. So also, as we expect, we end up with an overestimation of the wind speed. And after application of our correction value, again, the red line, we are quite good with compensating for these values. So the second part is uncertainty of wind speed estimates in the time series. So the uncertainty in each individual data point, what kind of error do we have there? And again, we did this parameter study and learned basically that this uncertainty is, first of all, it's 1 order of magnitude higher than the bias, so it's around 1 meter per second. And it's mainly caused by the fore-aft motion of the nacelle, which is in turn a result of the pitch rotational displacement of the floater. So consequently, we have high uncertainties for high pitch amplitudes and high pitch frequencies. So that's the cases where the nacelle moves back and forth fastest. And again, here we can think of what is the application, and do we need to correct for these effects. Time series lidar measurements are mainly used. Feed-forward control, of course, turbine load validation studies, load monitoring maybe, and also for studies where you constrain wind fields on actual measurements and use these constrained wind fields again for load validation studies, for example. And obviously, if we have these strong fluctuations here, so the blue line is an uncorrected measurement, then we can assume that there is effects from this motion influence for these applications. And here we tried a very simple correction approach, just applying a frequency filter. So if this motion influence is represented by one frequency, and we see this as a distinct peak here in the frequency spectrum, this pitch frequency, then the idea is just to filter this frequency region out, basically, or damp this frequency. And again, the results for the two floater types. So we see FlowGen, where this is the case. We have this strong pitch frequency around 10 seconds, so it's mostly wave excited, and we apply this frequency filter, and turns out that the correction is quite good. On the other hand, for Windcrete floater, obviously it does not pitch a lot. The pitch frequency is also much lower. This is it's not applicable, this approach, because we don't see a clear distinct peak in the frequency spectrum of the wind speed, so it does not make sense to try to filter this out. And we also see this in the in the error representation. So this is mean absolute error between the measurement values and the reference. And we see for FlowGen this strong influence here. So we have mean absolute errors in the range of 1 meter per second, or even a bit higher. And with application of this frequency filter, so the red line is again the corrected values, we are quite good with compensating for this effect. For the Windcrete, as I said, it does not really make sense, and this is also shown here in the error plots. In fact, we are increasing the error with applying a filter there, because it's basically we filter out relevant parts of the frequency spectrum of the wind itself. So that does not apply here. So conclusions: uncertainty in wind speed time series is mainly caused by fore-aft motion of the nacelle. The bias in mean wind speed estimates is mainly determined by the mean pitch angle of the turbine and the pitch amplitude. And we proposed a model-based correction approach for this, and showed this in a simulation environment at least. Of course, it's not validated in real measurements yet. And for the correction of time series, we also demonstrated the frequency filtering approach in a simulation environment. And we have recently published this study in an article, so if you're interested, you can have a look there. Thanks.
Thank you. Yes, first question.
Thank you for the presentation. I was wondering if for wind in offshore environment, it has been checked the spectra following a chimal or a MAN model properly, and if there is any publication that shows for the industry, maybe based on this kind of work, or maybe on a MedMast or something like that.
I think it's not really part of my work to do that, but there are, of course, studies doing that. I know there are people from DTU working on this, comparing time series of measurements in the Great Belt, for example, with different simulation models and spectra. So there are publications for that, but it's not really my work.
You didn't check it because I saw one PSD of the wind corrected, but you didn't try to see any spectrum behavior.
Yeah, so this is just based on simulation. So we assume in this work we just take one simulation approach for creating this synthetic turbulent wind fields, and we assume that's our ground truth. We do not validate that in the sense that we compare to real measurements.
Okay. Thank you.
Thanks for your presentation. I might have a question regarding the filtering approach. So obviously you have this big component that is due to the motion, but let's say now in the wind there is also a part of the energy that is contained into this frequency. How would you somehow separate the two?
It's a good question, and of course that's the main limitation. It works kind of good if you have the peak of the motion influence, the pitch, kind of far away from the high power region of the wind itself, let's say. But if you are like here, pitch is somewhere here, and also the highest power of the wind frequency spectrum itself is there. So you always have this problem. How do you design your filter, and where should it end? Basically, you don't know. So then you can just make some assumptions and say, yeah, it should somehow look like this, or it's a difficult problem. Yeah, I think in general this frequency filtering approach, it was a simple solution because we also wanted to use this data from FlowGen, and for that it works quite good, but it's not like a general solution to the problem.
Yeah, okay, thanks.
Any other questions? So I might have one. Usually we are interested in having the mean wind speed and also the turbulence intensity. So even if we know that the nacelle-mounted lidars might be not very accurate to measure the turbulence intensity, did you anyway try to look at the influence of the floating motions on the turbulence intensity assessment?
We didn't look into turbulence intensity specifically, because that opens up like a bit of another topic of measuring turbulence intensity with a lidar, and yeah, there are different questions. But of course, you can think of this uncertainty also as a representation of turbulence intensity. So the mean absolute error between reference and the measurement values is obviously increasing a lot here. So you can think of this maybe as added motion added turbulence. But we did not combine that with general turbulence intensity measurements. But yeah, of course, it's a good point. We should follow up on this and look into turbulence intensity.
Okay.
Thanks, Moritz, for the presentation. So especially here, we are looking at the vertical shear exponent versus pitch. Would it also make sense to look at horizontal exponent, horizontal shear versus roll?
You mean like weir?
Yes.
Yeah. I don't know. Probably for the offshore cases, there is not too much influence of that. Maybe if we think of wind farm setup where we are measuring in wake or something, it could be interesting. It could be implemented here easily. So if you have this represented either in your synthetic wind fields or for the analytical model, we also could implement this by integrating also a horizontal representation of shear. Could be interesting, but I think for the offshore cases it's not that relevant. Maybe more when you think of onshore and complex terrain setups.
But when looking at the errors, so we are not expecting any difference, do we?
That's a good point. I think it would be different effects if you think of combination of a horizontal sheared wind field and a nacelle moving back and forth. I could imagine that. I need to think about it, but that there are different effects. It also depends on how you reconstruct your wind speeds from the 4 measurements you have. There's reconstruction methods taking into account all this. So this is a 4-beam LiDAR, 4 measurements, and it depends how you combine them, and you end up with different effects of this motion. So it's an interesting question, but no direct answer.
Okay, thanks. Was enough for me.
Okay, thank you, Moritz.
Thanks.